Alright, so this is just going to be a simple example on how to find the work done by a force. So we've got a block here that's being pulled upward by this 10 Newton force at an angle of 30 degrees, and it's being pulled along in the, I suppose it would end up going in the positive x direction. So that's x and that's the y direction. And so let's find the work done by each force separately. So there are 1, 2, 3, 4 forces. Let's find the work done by each one in moving it. So let's find the work done if it's moved across a distance of, I don't know, 10 meters. Okay, and then it'll end up over here. So we know the distance is moved, we know this force, we know the coefficient of friction, we know the mass, and we know the angle. So we're looking for the work done by friction, the work done by normal force, the work done by gravity, and the work done by the force that's pulling it. So recall that in general, work is equal to the force times the distance times the cosine of the angle between the force and displacement. Alright, so let's start with F, the work done by the force F, shall we? So that will be the force, which I did call F, times the distance it's moving, so it's moving by a distance of d, 10 meters, times the cosine of the angle between the force and the distance. So the distance is in this direction, like that, and the force is pointing off that way, so the angle between the force and the distance actually is this 30 degrees. So that's the cosine of theta. Oh, it looks exactly like the definition I wrote. Anyways, so the work done by the force is the force, 10 newtons, times the distance, 10 meters, times the cosine of 30 degrees. Alright, well, we'll leave that for now. So now let's find the work done by, say, the normal force. So the force in this case is called N. The distance is still that d, that 10 meters it's moving. And the angle between normal force and the distance is 90 degrees. Can you see that? Normal force points straight up. The distance is straight to the side, so it's the cosine of 90 degrees. But the cosine of 90 degrees is 0, so that zeroes this entire term out. The work done by normal force is 0. Alright, now we'll see something similar for gravity, won't we? The work done by gravity is equal to the force of gravity times the distance times, well, there's 90 degrees between gravity and d as well. So the cosine of 90 is 0, and so the force, the work done by gravity is also 0. So that's an important point. If you have a force pointing perpendicular to a distance, the distance traveled, then that force is not doing any work because you have this 90 degrees, and the cosine of 90 degrees is 0. Alright. So next, let's find the work done by friction. So that would be the force of friction times the distance it's going times the cosine of the angle between them. So be careful here. See, distance is starting here and pointing in that direction. That's the displacement, the direction of displacement. Friction is pointing this way, the other direction. Now they're both lying flat, but the angle between them is not 0, it's 180. See that 180 degrees there? All the way from one side, rotated around to the other. So that's the cosine of 180. The cosine of 180 happens to be -1. So the work done by friction is the force of friction times the distance times -1, or I can put the negative out in front. Okay, but we don't actually know the force of friction, right? I wrote that in there, but we know like m and mu and stuff. We do know, though, that the force of friction is mu times normal force. So instead of friction, so we just recall the force of friction is mu times normal force. So instead of writing in friction, I'll write mu n times d. But we don't exactly know normal force, do we? And so that's where we have to look at our free body diagram and figure out what normal force is. Okay, so if we do Newton's second law, the sum of the forces in the y direction equals mass times acceleration in the y direction, then we should be able to solve for normal force, because normal force is in the y direction. All right, so it will be equal to 0 in this case, though, because it's not accelerating up or accelerating down. It's stuck on the surface. So the sum of the forces in the y direction is 0, but that's going to be equal to normal force, because normal force is positive y, minus the force of gravity, because it's pointing down, plus the y component of F. Let me make room here. So here is Fy pointing straight up. So that's plus the y component of that force that's pulling. And so if I rearrange this, I get that normal force is equal to the y component of the force of gravity minus the y component of the force. So y right there. And the y component of that force, if we analyze this force triangle, can be written as F sine of theta. So there is normal force. It's the force of gravity minus F sine theta. So I'll plug that in down here where I needed it in the work done by friction. So the work done by friction is equal to negative mu force of gravity minus F sine theta times d. And one more thing I can do, the force of gravity is just m times g. So the work done by friction is negative mu m times g minus F sine of theta times d. So we know all those values. So there's the work done by friction and the work done by the force. The work done by the force was very straightforward because we knew what the value of the force was, we knew how far it was going, and we knew the angle between them. The friction, well, it was a little bit more complicated, but in the beginning it is just the force times the distance times the cosine of the angle between them. The problem is we needed to define what friction is, right? Friction is mu times n, and in order to find n, we had to use our free body diagram and Newton's second law, and we found n. So we've done all of that before. So work itself is pretty simple. You just calculate it like this. And whatever you have to do to find the force, well, there's no way around that. But this is how you calculate work. And so there's the work done by friction, and there is the work done by the force.